So you have like 25 minutes plus 5 for discussion. I will tell you before 5 minutes before. And Chrysoula will tell us about extracting big gravity from string amplitudes. Chrysoula?
Right. Many thanks. Many thanks for this very kind invitation and opportunity to speak about this in Corfu. So I will speak about a project that I initiated and led and have been working on together with Dita Lust, who's there in the audience, Stefan Stipaga, and also Puria Mazlumi, the PhD student of Stefan Stipaga. So basically, let me take you on a trip from field theory to string theory and back, starting from ghost-free biometric theory, which describes interactions of spin-to fields with mass and no mass, so the graviton basically. Then we will move on to string states and consider and compute string scattering amplitudes in string theory. And then from them, we're going to go back to field theory through the extraction of effective actions from the string amplitudes. So let's start with Einstein's general relativity theory. So basically the theory that we understand as describing gravitation for us in space-time. We understand as a metric theory of gravity, but at the same time, due to many authors, it can be viewed from a particle theory point of view as the unique theory that describes the kinematics of the graviton of a massless spin-to field. From the string theory perspective, so let's say from a more fundamental framework that enables us to look at the quantum level at gravitation, in the case of closed string spectra, one may identify specific states that appear at the massless level in closed strings as the gravitons. So in particular, for example, here I give you the massless level that appears in bosonic closed strings, where the symmetric component corresponds precisely to the graviton as first suggested by Schack and Schwarz in 1974. Further, string scattering amplitudes of that particular state involving 3 and 4 external legs were computed, and from them the effective Lagrangians were extracted, which then gave rise to the expansion of the Einstein-Hilbert action, namely verifying that this massless state in closed strings interacts precisely as the graviton mode of the general relativity of Einstein. However, there's many questions that general relativity leaves unanswered. For example, that of dark matter, dark energy, the cosmological constant. And this is why modifications of general relativity, at least in the field theory side, are under investigation, have been under investigation for a long time. One particular very promising theory is ghost-free biometric theory. In particular, I give you here Hassan-Rosen action of ghost-free biometric theory, which involves two metrics, G and F, which are described, whose kinematics are described by two a priori independent Einstein and Hilbert actions, and which interact with this kind of potential, V, that I give here. It is a sum involving the so-called elementary symmetric polynomials. So some particular polynomials that are built out of the trace of this matrix S that is nothing other than the square root of G inverse times F. So this particular product of the two metrics. So we have two Einstein-Hilbert actions and a potential with no derivatives. And we have several parameters here, the two Planck masses, mg and mf, you see here, corresponding to the two metrics, and also 5 dimensionless parameters that enter the biometric potential. All right, now this kind of interaction was inspired by ghost-free massive gravity, so the theory of Deram, Kabadadze, and Tolley, that was first studied and constructed as the nonlinear extension of the interactions, self-interactions of the massive spin-to field that first Fitz and Pauli had written around Minkowski spacetime, but these authors, Deram, Kabadadze, and Tolley, extended this to the full nonlinear level around arbitrary backgrounds and in a ghost-free manner. So now, biometric theory propagates 7 degrees of freedom in total, as opposed to massive gravity, where around any background is just 5. And the point is that these 7 degrees of freedom do not necessarily split into those of the graviton and the massive spin 2 that is described in massive gravity. Now, given that this theory is very promising and that it describes, it contains the graviton of Einstein's theory, I started to think about how we can extract information on this particular potential that biometric theory involves, but from a more fundamental framework such as string theory, and in particular by looking at one of the few objects that are observable, and that is string theory. Those are string theory scattering amplitudes. So the idea is to try to extract information on this potential from string scattering amplitudes. And on this, we started working with Tita, Stefan, and Puria. And in particular, there's several steps that we had to take so as to try to extract information of this kind. We first had to treat biometric theory perturbatively, as we had to choose a particular background around which mass eigenstates are well defined. In the original biometric theory description, we have 7 propagating modes. As I told, we don't know which one is the graviton, which the other mass eigenstate mode. These are only well defined around particular backgrounds. Then we had to appropriately identify those states with string states, further compute, put them as external states on-shell string scattering amplitudes and compute those amplitudes, and finally extract the effective action from those. And in the field theory side, the first case in which we have non-trivial interactions in the expansion of biometric theory and Minkowski backgrounds, the simplest case, which is the one we're going to consider, is that of 3-point, so cubic interactions, 3-point interactions. And so we will compute 3-point scattering amplitudes. So let's look at the expansion. In the simplest case around Minkowski, we perturb both metrics. And in fact, this is well known. Other authors have constructed the interaction terms that arise around this particular background. And what happens is that at the quadratic level, combinations of the original 2 metrics. And in fact, one of the 2 it self-interacts. Its kinetic term is precisely that of the Einstein and Hilbert type. If you see here, this is the Lichnerowitz operator around Minkowski, namely the linearized Ricci scalar around Minkowski spacetime. Is that a question? I can hear. As far as the other state is concerned, the other mass eigenstate is concerned, again, it has kinetic term of the graviton type, so linearized Ricci on Minkowski, but it also has a mass term of the particular structure that fits have written, because this is the only graviton that one can write for a spin 2 field, that one can write around Minkowski. I think I can hear my voice or someone speaking from the audience. Sorry, thanks. So in this particular case, that one obtains this mass term for the spin 2 from the expansion of biometric theory, the Fritz-Pauli mass depends on the parameters, nothing else other than the parameters of biometric theory. So you see here one of the 2 Planck scales, the ratio, the dimensionless ratio of the 2 Planck scales, and also some of the beta parameters. Sorry, I can hear my voice again from the audience. Ruben, thanks. Right, so this Fritz-Pauli mass term is a mass, involves a mass that depends precisely on these parameters of biometric theory. And in fact, more interestingly, this massive mode has been put forward as a dark matter candidate. If we can discuss this later if you want, it has properties precisely of the dark matter kind, at least for some region of the parameter space of biometric theory. And as these authors here have suggested and investigated, it can play the role of a dark matter particle. Now, as far as the cubic interactions that are concerned, I give you here the full term that one gets from the expansion when it comes to interacting the interacting graviton and the interacting massive spin 2 states. So with G capital, remember, is the graviton, M capital is the massive spin 2. And these are all terms describing from biometric theory at cubic level their interactions. And you see there are very many terms in the coefficients, the couplings depend on the parameters of biometric theory. Let me summarize here for you what these the previous authors that suggested this dark matter candidate, this massive spin 2 as the dark matter candidate, see at the cubic level as far as the interactions of G and M are concerned. Remember, G is the graviton, M the massive spin 2. So for both G and M, for both their self-interactions, one finds two derivative terms that are precisely of the linearized Ricci scale type, scalar type, around Minkowski spacetime at the cubic level. And further, M has a non-derivative term that is related to the fact that it has a mass, whereas G, the graviton, does not have one. Then we also have the GM square interaction that I showed you in the previous slide, which involves both non-derivative and two derivative terms. The fact that G, the graviton, in this particular case, at both the quadratic and the cubic level, has self-interactions solely of the GR type, means that it can be identified with the graviton. And in fact, the authors that I mentioned before here, let me go back again, argue that this can be extended to the full nonlinear level. And so G can be identified even nonlinearly with the graviton. At least there's arguments in favor. What is important to stress here is that I gave you these three kinds of vertices, but not the G square M, so two gravitons and one massive spin 2 field interacting, because in biometric theory, at least in this expansion around Minkowski, there is no such term. There is no kind of interaction involving a massive spin 2 that decays into gravitons. And this is a discriminatory feature of, at least phenomenologically speaking, of biometric theory, of this particular biometric theory compared to other kinds. Now, when it comes to computing string scattering amplitudes, which is our main goal here, the way to compute on-shell such amplitudes is by using vertex operators that correspond to the particular states one uses as external states in the amplitude, and those satisfy specific relations because of BRST invariance. And there's the so-called on-shell relations, on-shell conditions, and in particular, they're the kind of the mass being on-shell and the mode, the respective state, being both transverse and traceless. So in the string side, one has these conditions imposed on the states that one uses in one scaters. This means that if we're to compare in a well-defined manner field theory and string theory, at least the field theory extracted from string theory in the low energy limit, then we have to impose the very same conditions also in the field theory side. And so this brings us to these equations, namely that both G and M have to satisfy the Klein-Gordon massless for G and massive for M equation. And further, that they have to be transverse and traceless, which in the case of the graviton leaves us with 2 propagating degrees of freedom, and in the case of the massive spin 2 with 5, as is very much expected for massless and massive spin 2 propagating modes. So by imposing these conditions in the field theory vertices, so the cubic interaction vertices I showed to you before that one expects at this level for biometric theory, we managed to reduce all kinds of interactions to this set of terms. You see here self-interactions of the graviton, interactions of G with 2 massive spin 2s, and self-interactions of the massive spin 2. And what you see here is actually that modulo that G square M interaction that is not present, at least in the cubic level of biometric theory. All other kinds of terms that I present to you here are all possible Lorentz invariant terms that one can write involving transverse and traceless, massless and massive spin 2 tensors. So the structure of the terms that we have here is not entirely unique to ghost-free biometric theory. However, the particular coefficients, the way the couplings depend on the coefficients, on the parameters that appear in ghost-free biometric theory is unique. You see here, for example, the coupling of the non-derivative self-interaction mass term at the cubic level of the massive spin 2, and it depends in a very specific manner on 2 of the dimensionless parameters of the biometric potential. So basically what I just said is summarized here. And one important point that we can stress is that the only kind of non-derivative terms that survive the on-shell conditions are those that involve only massive spin 2, the massive spin 2 mode. So a term, so here the trace is meant with these brackets, the term that involves no derivatives and one graviton and two massive spin 2 modes disappears after one imposes the on-shell conditions. All right, so we have managed to bring our field theory vertices into such a structure that can be comparable with the string prediction. Which brings us to the string scale, to the calculation of the string scattering amplitudes. And first important step is to identify the two modes that I've been referring to, the graviton and the massive spin 2, suitably with string modes, string states in the string spectrum. Now, as is clear, and as I also mentioned in the first slide, the graviton is universally identified with a closed string state, all right? A massless symmetric state that appears in all closed string spectrum. Can you hear me? I get a message here that, okay. Now, however, for the massive spin, thanks. When it comes to the massive spin 2 state, one has to make a choice. One has to choose, has to scan the string spectra that are available to us already from since decades. One of these states, of the massive spin 2 states, because there's several, if one looks at the spectra of the towers in both closed and open strings in many kinds and different kinds of theories, so type 2b, even heterotic, one comes across a massive spin 2 state. So one has to really make this choice as to which one is the one that appears in biometric theory. And we started, inspired by previous work by Dita with Sergio Ferrara and Alex Quejallas. We started with the open string spectrum of type 2 type 2 strings. And there, the first massive level that one encounters, built out of these kinds of oscillators acting in the vacuum, one sees that there is a symmetric massive rank 2 tensor, and which has a mass that is given by 1 over alpha prime, where alpha prime here, not to be confused with the alpha prime I showed you before, the ratio of point masses in the field theory side. Here, alpha prime is a string scale. All right. So if we make this identification, if we choose to make this identification, we are forced, at least a priori, to make this identification between the Fitz-Pauli mass of the massive spin 2 mode as predicted by ghost-free biometric theory, and the mass of the massive spin 2 state in the open string spectrum as given in terms of alpha prime, the string scale. All right. So let's start with this choice. The next step is to calculate string amplitudes. And how does one perform this task? By constructing the respective vertex operator that corresponds to the graviton and the massive spin 2 state I showed to you. And here I give you the master formula for such an amplitude. It is nothing other than the correlation function of the various vertex operators that correspond to the external states of a string scattering amplitude, integrated over the world sheet, because the specific position, specific point in the world sheet where a string state is created is not physical, so one has to integrate. Now, compared to previous studies, our novelty when it comes to calculating such amplitude is that we use only rank 2 tensors in the external legs, which has never been done before. And further, that at least 2 of the external states we use are massive. And these 2 points complicate both the calculations to some extent, but also the extraction of the effective actions. And to calculate such a correlation function, one has to, as I told you, construct the vertex operators. For the graviton, it is very well known what that is in the 0.0 ghost picture, and it is built using the space-time coordinates x mu and psi mu from the worldsheet point of view for bosonic and fermionic respectively. And also you see here the polarization tensor of the graviton, and you see here further where Q, with Q being the momentum of the state of the graviton is thought of as heavy. It has to satisfy this Q has to satisfy the on-shell conditions that I told you before. So you see here transversality, the mass shell condition, symmetricity, the fact that it's a symmetric representation of the Lorentz group, and also tracelessness. A similar construction can be made for the case of the massive spin-2 state. And now for K being the respective momentum and alpha being the respective polarization tensor, again, you see the on-shell conditions. So transversality and symmetricity, tracelessness, and now here the on-shell condition, which tells you that the mass is, or the mass square is proportional to 1/4 alpha prime being, as I said, the string scale. All right, so we need to use these kinds of vertex operators and appropriately put them inside the correlation function. Appropriately means that the ghost picture has to be chosen such that the full amplitude, how to explain this? The several kinds of pictures exist. So an operator, in fact, that corresponds to a particular state can be written in several kinds of ways, depending on how one wants to choose to put the ghost charge, to assign the ghost charge in this particular state. But in fact, at the level of the amplitude, it doesn't matter. The full amplitude should not depend on how you choose, how you make this choice, so long as the sum of the vertex operators ghost charges cancels the background charge of the respective topology, which in our case is the disk. So there is some ambiguity, but in the same time, there's many kinds of ways the full amplitude is to be independent of the ghost picture. So for example, for the amplitude involving the scattering, describing the scattering of one graviton to a massive spin-2 states. So if you remember GM squared from the field theory perspective, one may write this kind of code.
Have like 5 minutes. Thank you.
So one may write this kind of correlation function, and one further has to take into account the fact that the brain is thought of as being super heavy, which means that momentum conservation only makes sense along the brain directions. Further, it is possible to define Mandelson variables, even though it is a 3-point scattering amplitude. One may regard the closed string in both, when it comes to both computing via Wick's theorem, the correlation function, and also the kinematics of this particular process. One can regard the closed string as two open strings, and so assign two different kinds of open string momenta to this closed string that are related via the so-called D matrix here, which encodes the information on the boundary that the brain is putting. And so using this one may, in the end, it turns out that there is a single kinematic invariant, which depends on the open string momentum in this particular representation and the string scale, alpha prime. And one may further, as we did, compute the full string scattering amplitude. I give you here one particular way that we used to write the result. So we wrote it as a sum for different kinds of grouped terms that involve kinematic packages. So here, let's give you one example of one simple kinematic package that involves momenta and the D matrix, so momenta of the external states and the D matrix, and also the alpha prime. And also you see that there's integrals involved because of the fact that we have integrated over the world sheet. And in fact, it turns out that there's 36 of these kinematic packages. We have computed all of them, and we have managed to write the result after partial fraction and evaluation of the integrals in a compact way. Let me give you just one of the grouped terms that in the final result is given as here. So it's basically, again, a sum of terms involving kinematics. One example is here. So momenta, you can think of it as involving the momenta and polarization tensors times some gamma functions, products, and more complicated forms of gamma functions that are due to the integrals. So schematically, we have kinematics times something that comes from the integral. Now, when it comes to three massive spin-2 states, we have performed a similar calculation and come up with this result. the point is that already here, if one compares, which is what we did, this kind of amplitude with a 3 gravity amplitude that has a universal form, at least when it comes to 2 derivative terms from string theory. And what one sees is that these coefficients that I give here in orange are not the same in the case of the massive spin to state and in the case of the graviton. So already we see that when it comes to 2 derivative terms, the massive spin to mode and the graviton, at least the massive spin to mode we have used from the open string spectrum, interact differently, self-interact differently. Now, back to GM square, to deduce the low energy effective action, we made first some simplifications, namely we used the identity matrix for the D matrix, the boundary matrix that encodes the brain information, and also restricted ourselves to the U1 gauge group when it comes to the gauge group of the brain. Then the question raised itself as to how we're going to take the low energy limit and extract the effective action, because if you remember in string theory, when one has massive states in the external legs, one takes alpha prime to be very, very small and arrives at low energy actions after identifying the polarization tensors and momenta with fields and derivatives respectively. In our case, this cannot be done because the mass also depends on alpha prime, the mass of the massive string state that we used. Remember, it's 1 over alpha prime. So if you send alpha prime to 0, then this mass diverges. So this limit has to be taken with care. In particular, what we find is that we need to use a particular representation of the Mandelstam variable S in terms of 1 open and 1 closed string momentum, in the case of the amplitude that involves 1 gravity and 2 massive spin to states always. And then the appropriate limit, let me go one step back, is the one in which S goes to 0. At the same time that alpha prime, so to speak, goes to 0 as well. So after making the substitution of S inside the result of the amplitude, and also performing the simplifications of the D matrix and the U1 gauge group I told you, and then keeping only terms up to order alpha prime, we managed to write all terms that we calculated up to 2 derivative interactions involving 1 gravity and 2 massive spin to states. Now, to compare with the field theory, we're almost ready. We just need to, let's say, make this identification again between the polarization tensors and the fields and momenta and derivatives. And our results are summarized here. These are the actions that we extracted for the graviton at the QP level, GM square, and the massive spin 2 from the open string spectrum, remember, at the cubic level as well. And the structure, again, is very much the same. If you remember what I showed to you from the field theory perspective, at least from the biometric theory perspective, we get the very same set of terms. At the same time, however, the coefficients do not match. In particular, here, we obtain 1 instead of a 2. And here, we obtain a 3 instead of a 2. What I say instead, I mean compared to biometric theory, close to biometric theory. So what this means is that we have a massive state, the one that we have used. It describes in terms of interaction terms, it interacts in terms of vertices in the exact same way as the massive spin to mode from biometric theory does with the graviton, but the coefficients do not match in both the interactions of GM squared, of the kind of GM squared, and the sub-interactions of M. In particular, if looking more closely at the interactions of M, the self-interactions of M, what we observe is that they are not of the general relativity Einstein-Hilbert type. So the particular coefficient mismatch tells us that at the cubic level at least, this massive spin to mode does not self-interact as the graviton of Einstein's theory does. Whereas in biometric theory, both modes, even both the masses and the massive mode, are predicted to be interacting like a graviton, self-interacted like a graviton. And here at this point, perhaps it's instructive to notice and stress that this the discrepancy we find, the 3 that should be 2 in biometric theory, but one of the particular coefficients of the self-interactions of M is is reminiscent of very similar 2 versus 3 discrepancy that appears in the case of the Van Damme-Veltman-Zakharov discontinuity, where, if you remember, if one considers the massive spin-2 propagator and takes the masses limit, so here I'm talking about field theory again, propagator of the massive spin-2 of Fitz-Pauli, take the mass to 0, what one finds is that up to singular terms, the propagator is written as a sum of 2 terms, which are very much the same as that of the graviton, up to this coefficient here. So in the case of the graviton, this is 1/2, whereas in the massless limit of the massive spin 2 Fitz-Pauli, it's 1/3. So we see here a very similar discrepancy, which I have to stress is different in origin, as in our case, we see that the kinematic terms are not GR-like. So the cubic self-interactions are not of a GR type, whereas in the case of the Van Damme-Veltman-Zakharov, this 1/2 versus 1/3 discrepancy is solely due to the fact that there's a mass term in the case of the Fitz-Pauli. So what we gather from all this, what we conclude, is that the open string state that we have used is not a suitable candidate for the massive spin-2 mode of ghost-free biometric theory around Coffsey backgrounds. However, we have described fully for the first time the full set of interactions of this open string state with the graviton and with itself up to cubic level, which nobody had performed before or explored before. And now at the moment, we're investigating the possibility of the massive spin-2 mode of ghost-free biometric theory coming, if you prefer, from the closed string sector, which brings me to the end of my presentation. Thank you very much.
Thank you, Chrysoula, for your nice talk. Do we have a question here in auditorium in Corfu? No. Do we have some online questions, maybe? No, there are no online questions. Then let's take. Yeah, sorry. There is a question here, Roberto.
Hi, Chrysoula. Thanks for the nice talk. So if you find that also a closed string does not give the right amplitude, then what would you conclude? That you have to look somewhere else, or that this theory is in the swampland, or what?
Okay, so our preliminary evidence already shows, I'm very optimistic that the closed string actually will be able to play this role of the massive spin-2 in biometric theory. However, if you want more philosophically, the idea was that we try somehow to see if there's an embedding. Actually, my first goal was to try to see if we can determine the parameters, the beta parameters of biometric theory from the string. Now, if this turns out in theory, in principle, let's say, not possible, what we gather is that we have some states in strings that we know now, also massive states, how they interact with the graviton. We explained this for the first time. Whereas ghost-free biometric theory, at least from this kind of perspective, cannot be embedded. Now, I'm not sure whether one in that particular case, which I don't think is going to be the case in the end, one would conclude that biometric theory cannot be embedded more generally because we use a very particular background, the Minkowski background, and we use that mass against state base up to a cubic order. Biometric theory, the full action, if you want to let me go back, it's written around, sorry for being, it's written around arbitrary backgrounds. And you see that here it's the full nonlinear theory involving 2 metrics. And as I stressed before, here we don't have a split into mass against state. So we don't even F as masses and mass. It doesn't make sense to ask this question. Maybe let me put it this way here. So even if we, in some hypothetical scenario, find no kind of embedding from the string scattering amplitude point of view, I wouldn't necessarily argue that this can be extended to as a comment of the kind that biometric theory cannot be embedded, because the full biometric theory is the full nonlinear with no well-defined mass against states. Right. Does this answer your question?
Yeah, thank you.
Thank you.
It's conceivable to also calculate the 4-point functions.
Excuse me?
From the strings.
Sorry, I couldn't catch that. Could you repeat that, please?
Is it conceivable to calculate also the 4-point function from the strings?
Okay. So whether it would give us more information. So in the case of the open string state that we used, it probably would, but at the same time, deduce information because we have this the discrepancy. So the 4-point would be much more useful in the case of the closed strings. So if we succeed with a cubic level, then perhaps the 4-point would also give more, give additional information. Yes, thank you.
Thanks.
Yeah, thank you.
So if there are no more questions, there is a question.
So there were a bunch of papers from a long time ago by Massimo Torona that I thought calculated the 3-point amplitudes from among the first Reggie trajectory of the string. Was that not what you needed? Or?
Sorry, which paper by Torona? I didn't mention that.
Yeah, Massimo Torona.
Sorry, I cannot hear you. Can you repeat that, please? I didn't mention any paper by Torona.
Yeah, I'm wondering.
Oh, okay. You're wondering. Sorry, I couldn't catch that. Yeah, can you repeat? So then, what was it? What was the question?
I thought you computed the 3-point amplitudes from among the whole first Reggie trajectory.
Okay. In what string theory was that? I'm not familiar with this. Sorry. Sorry, what's that?
Just the open and closed bosonic strings.
Open boson. Look, the state that we use is unique in open string type 2 theory. Is that the same that they used in Tarona's paper? Is that what you're saying? Because I'm not familiar with that paper, so I cannot.
That's what I'm wondering. I'm not sure.
Okay. It's a question. So I have to look at this paper to tell you if it's the same state. It should be. It's unique, and the vertex operator up to the close picture is unique, so it should be the same. But it doesn't sound like that to me. I have to look at the paper.
Good. Thank you.
No, thank you.
Okay, thank you, Chrysoula. Please let's thank Chrysoula once more.
Thank you.
And now we are moving on to the next speaker, who is also online. Ioannis Lavdas. Ioannis, do you hear us?
Yes, I can hear you, but I cannot start the video because I'm not authorized. Let's see.
And now you should be able to share your screen, maybe. We see you now.
Okay. I cannot see you, but
No.
second. Yes. Okay. Shall I share my screen?
Yes, please.
Yes, I should put it perhaps on. Second.
Okay, we see your screen. Just make it full screen, maybe.
Yes. Like
You have 25 minutes plus 5 for discussion. I will tell you 5 minutes before. And the next speaker is Ioannis Lavdas. He will tell us about entanglement islands, ADS, massive gravity, and holography. Please, Ioannis.
Great. Thank you very much. Let me start by thanking the organizers, Professor Zupanos and the organizers, for this opportunity to speak in this workshop. It's really an honor. Thank you very much. So I would like to present to you in this talk, a work in progress. This collaboration with Professor Lust and my fellow postdocs from Munich, Saskia de Muider and Alessandra Agnecchi. Now this work regards the behavior of entanglement islands in a very specific string theory setup, which allows for massive gravitons and has a very well-defined holographic dual. So our motivation practically comes from this well-known series of recent developments on methods for calculating the entropy of Hawking radiation in a plethora of holographic setups. And all these share a common feature, and this is the large corrections to the entanglement entropy of the radiation region for an evaporating black hole that actually render the process consistent with the unitary black hole evaporation. And this region that contributes is spatially disconnected by the radiation region, is far from it, and it's called the island. It belongs in the gravitational system. It lies behind the horizon and also outside the horizon. So these works practically started in 2 dimensions with examples on JT gravity coupled to external baths, but they were quickly extended in higher dimensions, and the prominent role in this case is played by Carr-Handel configurations, which realize high-dimensional setups of black holes coupled to external non-gravitating or weakly gravitating baths. Also, an important recent development is an uplift of these Carr-Handel configurations in string theory, and provides actually a UV embedding of these setup, realizing all the qualitative features that are met in these configurations. And now, our main motivation, therefore, is these uplifts, and we have already some results in this class of solutions regarding spatial geometries in this context that allow for a graviton mass, that have very well-defined 3D duals, and would like actually to extend the results that we have in this context by studying the behavior of island surfaces in spatial limits of the geometry that we already know how they behave, see the role of the graviton mass, and approach these very interesting questions from a quantum field theoretical perspective. So let me start with the Carr-Handel brane worlds. Practically, one second, because can you see my cursor, by the way? Because I cannot see it.
No, we don't see it for some reason.
Yes. Okay. I don't. If it's not a problem, I can continue like this. But I realized I cannot see it. So if you don't mind, I can continue like this without a cursor.
Yeah, it's fine.
Okay. So yes, I start from the Carr-Handel brane worlds, which is as I said, is very central in this discussion. So we start from an ADS5 bulk in this case, and we consider a slicing by ADS4 slices. Okay, we consider a slice of ADS4 intersecting the bulk intersecting the boundary practically on this blue point that I have in the picture. This is the conformal boundary of ADS5. So the introduction of this brane imposes a UV cutoff. So the left part, the white part, is removed. So one here has exactly the context needed to study a problem of a black hole on the brane coupled to a non-gravitating bath with transparent boundary conditions. The only thing that has to be made is to follow this construction, this funnel that I give here in the picture, and address the question for the position of the radiation region, the position of the island, and so on and so forth. So the important thing here is that the radiation region is found on the conformal boundary in a non-gravitational region. So it can be chosen because the Hilbert space on the boundary can be factorized. Now, on the other hand, the point on the brane, on the island, is not externally imposed like in the radiation region, but dynamically, because we need to be chosen in order to minimize the area of the surface that connects the two boundaries, the boundary of the radiation region and the boundary of the island. So the virtue of these constructions is that they admit equivalent holographic descriptions, and I have put them there in boxes. We have either four-dimensional CFT on the half space, coupled to some boundary degrees of freedom, some 3D CFT. We can either have the fully geometric description with gravity on ADS5 and gravity on the end of the world brane, and also the last one, which is CFT with some intrinsic UV cutoff on the brane, coupled to ADS gravity. And this coupled with transparent boundary conditions on the CFT on the half space. Now, this is exactly the setup that is used, and the first thing that is about to be calculated after setting up the configuration is the choice of the Ryu-Takayanagi surfaces that will be used for to compute the entanglement entropy. So there are two classes of bulk Ryu-Takayanagi surfaces. The one is the one that you see starting from the boundary of the radiation region and crossing the horizon. This is called Hartmann-Maldacena surface. Practically, it ends up on the corresponding point in the thermofield double. It's a double setup. And the other one is the island surface connecting the boundary of the radiation region to the boundary of the island. Now, it turns out that at initial times, the Hartmann-Maldacena surface is the one that dominates. So it's the one with the smallest area. So practically, the island surface at early times has the largest area, but its area is constant because it has nothing to do with the area behind the horizon. On the other hand, the Hartmann-Maldacena surface crosses the horizon, so crosses the Einstein-Rosen bridge. So along with time evolution, is stretched. So its area is giving this unbounded growth of the entropy. Now, once this meets actually the area becomes equal with the area of the island dominates because it starts having the smallest area, and therefore it bounds this growth of the entropy that is given by this introduced by the Hartmann-Maldacena surface. This is seen in this page-like curve that we have on the right hand side of the slide. So this practically evades problems with unbounded entropy. Now, a very important thing is that here the radiation region is found in a non-gravitational region, and it tremendously changes if one considers a weakly gravitating bath. In this case, this is realized in the Karl-Randall setup by a brain entering slightly in the bulk with a small angle that I have written here as right theta. So in this case, the thing that changes is that the surface now cannot be determined externally. The radiation region, cannot be determined externally because in a gravitational system, we have no diffeomorphism invariant way to factorize the sectors. Therefore, both the endpoint on the radiation region and the endpoint on the island have to be dynamically set, dynamically chosen. In this case, this ends up to a Ryu-Takayanagi surface that settles on the horizon of the black hole if I have this black string background, or entering the ADS5 if I have empty ADS. So in this case, we have a trivial page curve, but there are other objects that may have a page curve behavior. So before I go to that, I would like to say that this shows that the previous result shows that the full information is accessible somewhere, and this somewhere is the defect where the two branes meet. Okay, and this has quite a similarity with the evaporation in the asymptotic in the flat space, but this is another discussion. So the quantities now that exhibit a page curve actually are given by surfaces that are anchored on this defect on the boundary, which is again a non-gravitational region, and the one passes through the horizon, constituting a Hartmann-Maldacena surface, and the other one shooting to one of the two branes. Now, the fact that we have a theory on the 3D boundary, on the 3D defect on the boundary, means that I can consider factorization of the Hilbert space. So I can define another kind of entropy, a different kind of entropy, called left-right, which actually correlates degrees of freedom on the one brane with degrees of freedom on the one sector of the theory on the boundary. So these are the two distinctions, and we see here how much crucial is whether my bath is quickly gravitating or not. Now, these are the two results that were uplifted in string theory by this recent work of Uleman. And the basis of this recent work, I will be very quick in this, is a string theory version of this model is based on these solutions in type 2B string theory. These are actually ADS4 fibers over a 6-dimensional base manifold that has this form, is just a product of two spheres wrapped over a Riemann surface. And the form of the solution is the one in the box. We have a metric, then a solution on the strip on the Riemann surface is labeled by two harmonic functions. And these actually metric factors that you see in the metric are functions of the harmonic functions h and h hat. The solution finally has three forms and 5-form field strengths, which actually will result to non-vanishing fluxes in the solution. In the box, you see the form of the harmonic functions, and the most important thing that we will say now is that they actually have some point singularities on the two boundaries of the strip, which, by the way, are boundaries on the strip and not on the geometry. And this is because along the fiber, the radii of the two spheres are allowed to vary, and they vanish actually on the two boundaries of the strip. Now, these singularities support non-vanishing fluxes. You see here 3-form Neve-Schwarz, and 3-form Ramon-Ramon fluxes, and moreover 5-form fluxes, which actually signal the presence of 5 brane stacks, D5 or NS5, and 3 branes connecting them in the geometry. So practically the image of this geometry actually can be given by a brane configuration, or it can be seen as a near horizon geometry of a configuration of intersecting D3, D5, and NS5 branes. Now, the semi-infinite D3 branes that you see on the right and the left over here correspond to the asymptotics of the geometry. So practically you can think of the solutions as a domain wall in ADS5 S5. So right and the left we have asymptotically ADS5 S5. And there are two interesting limits. The one is the limit that corresponds to a boundary CFT, where the one asymptotic is capped off and the other is the other remains. This is a smooth limit. And the second smooth limit that is interesting is where both asymptotics are capped off, and its dual is not anymore a boundary CFT, but rather a 3-dimensional n equals 4 square conformal field theory. Now, these limits are important because these are exactly the limits which will be used to model black holes coupled to baths. Now, for the non-gravitating bath, we have the first limit is used, where one region is capped off and the other remains. And the black hole will be actually located in the region of the 5 branes in the smooth interior, while the bath will be found in the asymptotic ADS5 S5. The thing that one has to do is first introduce a black hole by substituting the ADS4 with an ADS4 black hole, which is completely valid here. And we see here that we have this new form of the 4-dimensional metric with the horizon at RH. So, 1 second. Can you see my full screen, or you see the window of Zoom?
Sorry, I didn't hear your question.
Sorry, my question is, can you see my full screen, or the Zoom window is blocking elements of the slides all this time?
Well, we have just your video in upper right corner, and I don't think it's blocking anything.
Okay. So it's my okay. So I see. Okay. So it's my problem. Okay, good. Very well. So as I was saying, first the ADS4 is substituted by an ADS4 black hole, and then one considers the island surface by considering surfaces wrapping the spatial part of the ADs for black hole, the two spheres and a part of the Riemann surface. Actually, it's specified by this embedding function, which depends on the coordinates of the strip, x and y. And then its area is computed and it's extremized. So the area is extracted by this extremization. In this paper of Ullmann, the whole thing is numerical, it's not analytical. So the next thing that is done is that boundary conditions are imposed. So this island surface should anchor at some point on the radiation region. It should extend along the strip and closes smoothly at the regular interior point on the left of the strip. So yes, exactly. The boundary conditions actually are imposed so that we don't have any kind of conical singularity on the two boundaries of the strip, on the capping, on the point that caps off. So their Neumann boundary conditions are imposed. We have Dirichlet boundary condition that is imposed on the ADS5S5 region, because the surface should anchor on the radiation region over there. And finally, last but not least, we have the contribution from the near pole neighborhoods, which actually have a finite contribution to the area, but the metric over there, okay, is singular, as it should be around the brane. Now, a similar analysis is followed for the Hartmann-Maldacena surfaces, with the difference that we should pay attention on how it intersects the horizon. And then the next actually step is to see how these surfaces evolve. This again numerically by introducing some auxiliary time parameter to induce evolution. And the final thing that we see is, the result that we see is this. On the left, we have the island surface. We see that it anchors on the bath region, or the radiation region at some point in the bath, and then enters and spans the strip where it caps off at the poles and is regular, smooth and regular at the interior. An important thing that we see that is in agreement with the Karch-Randall setups is the fact that if I consider actually anchoring point closer to the horizon, then the whole surface goes closer to the horizon. It is something that is evident from the Karch-Randall setup. Now, the second picture on the right is exactly the Hartmann-Maldacena surface. You see that it intersects the horizon at zero. And I think that we actually recognize also from the Karch-Randall setup is that it never approaches the 5 brane regions. So it never bulges in the strip close to the regions of the 5 branes. So as a matter of fact, we have seen in the setup with the Karch-Randall branes that the surface remains always away from the end of the world brane. So the next step is to actually see the difference between the areas of these surfaces and see if you have a page curve or not. Okay, yes.
Sorry, Ioannis, you have 5 minutes left.
5 minutes. Okay. So in any case, we see a page curve because again, like in the other setups, we see that the Hartmann-Maldacena dominates at zero at early times and the island at late times. And this actually shows that the ratio in which the solution behaves, which is the ratio between the boundary and the bulk degrees of freedom, corresponds to this angle that I was saying in the beginning. And we have also to underline that we have a critical value of this angle above which there are no islands, and we see exactly a critical value in this setup for this ratio of the D3 branes, of the suspended and the semi-infinite ones. Now, I will be very quick here we have exactly done, we have results in this setup where the geometry gives a massive graviton, and we have extracted again a formula for the mass of the graviton, which depends on the degrees of freedom, or the ratio of degrees of freedom of the four-dimensional bulk over the three-dimensional degrees of freedom, which is actually the inverse of this ratio which characterizes the embedding. So we see that we need a large ratio in the above embeddings in order to have a small graviton mass, but this ratio should be still smaller than the critical value in order to have islands. So we are trying actually now to quantify this as a statement for the mass of the graviton itself. The other thing is the last thing that I will refer to is the following. We referred at the beginning for the gravitation on the gravitational buff. Now, the uplift of this gravitational buff corresponds to the fully capped off solution. Okay, and in this case, the island stretches from -infinity to +infinity and settles in the horizon. So we were actually giving a non-trivial page curve, a trivial page curve, sorry, without time dependence, therefore. So we're trying to see if this can be associated to a parameter that labels the mass of the graviton, which is the variation of the dilaton. Practically, an interesting limit is the limit of very large variation of the dilaton, because the value at infinity that I write here is a free parameter that I can choose. So we know that for big variation of the dilaton, actually the mass goes to zero. The throat decouples that I have here, and I find myself in a compact geometry with a massless graviton. So this limit signals a transition from the non-gravitational to the gravitational buff, and we have tried to see this with numerics from which we have strong indications that in this, if we use explicitly in the numerics the variation of the dilaton, the island surface, we have indications that approaches the horizon, and therefore we have a transition from the one type of buff to the other. Finally, and I'm closing with this, there are, as I said in the beginning, there are other objects that exhibit page curve behavior, and actually this has to do with the factorization of the three-dimensional theory in the Karl-Randall models. Here, it has a very similar effect. It factorizes somehow the overall quiver, the overall initial 3D equals 4 theory into sub-theories. And we have made, we have seen in the work that in a limit where the geometry factorizes, actually the initial quiver factorizes into two sub-quivers, and therefore what we are trying to do right now is to consider entanglement between these two sub-quivers. So this would be a computation that would be complementary to the present one. So I'm closing by summarizing. I presented some string theory uplifts of Karl-Randall configurations, realizing for the gravity coupled to external buff. Now, in these embeddings, actually, we see all the features that are exhibited in the Karl-Randall models now in a UV complete setup, and we have seen how islands and Hartmann-Maldacena surfaces emerge and how page curves are formed in this context. Now, the questions that I just would like to underline is what we are doing now. We are studying the behavior of the surfaces at special limits of the geometry, and we are approaching the basic questions about the existence of the surfaces from a quantum free theoretical approach. I hope I'm in time. Thank you very much for your attention.
Thank you very much for a nice presentation. Do we have questions in the audience? Yes, we do.
Yes, hi, Ioannis. Two very simple questions.
Yes.
I was confused about where the black hole evaporates to. So you have a black hole on one brane, and then when it evaporates, does it go to the center of the ADS5 process 5, or does it go out to infinity? And then I have a second question, but can you answer?
Yes, this goes, no, this, 1 second, let me show you the setup. Yes, in the first case, actually, it goes to infinity, the one. So it gives a page curve. The black hole is found in the region around the 5 branes and the smooth interior, and the radiation goes at ADS5 as 5. Not remains. It doesn't remain.
Boundary of ADS5.
And
not to the center of ADS5.
No, the boundary.
I see.
And
are curves classical Ryu-Takayanagi curves or quantum? Is there any quantum correction to them? In the string theory uplift.
Okay. Because in the Karch-Randall, these are designed to be classical, right? This configuration.
Right.
Yes.
In your calculation, it's also classical, or there is a quantum correction?
Well, the calculation is based on classical surfaces. You mean the calculation on the string?
The numerics you talked about. It's all classical minimizing of a surface.
Yes.
Okay, thank you. Yeah.
You're welcome.
Thank you. Any more questions from auditorium here? No? Do we have some online questions maybe? No, since there are no more questions, let's thank Ioannis again for this nice presentation.
Thank you very much.
And now we are moving to the next talk, which will be on site here in Corfu. Next speaker is Ruben Minasian, and he will tell us about Ruben is going to tell us about anomalies as obstructions from dimensional lifts to swampland.
Thank you.
Ruben, you have 35 plus 5 and 5 signal.
Okay, thank you very much. It's very nice to be here, and it's a particular pleasure to be able to give this talk in person. So this is work based on collaboration with the, in collaboration with the very extremely good graduate student Cheng and with Stefan Tyson. And this is particularly appropriate for this forum because Stefan has been not only a great friend and collaborator of many years, but he was also my Humboldt host many years ago in Albert Einstein Institute, which is an absolutely fantastic institute and where the research environment is very stimulating. I should also add this occasion that I am very pleased to be able to host a Humboldt fellow myself now in Paris, and Humboldt administration has been absolutely fantastic. Responsive, flexible, and genuinely willing and able to help. So I will, for the purpose of this talk, exclusively concentrating on 6-dimensional 1-0 theories, minimal supersymmetry. So here is the bosonic little group, different representations of gravity multiplets, and the basic players are the gravity, tensor, Young-Mills, and hypermultiplets. You see the fields in red. These are the chiral bosonic fields, self-dual and anti-self-dual tensor fields. And in blue, the fermionic chiral fields. So everything is chiral, everything is anomalies. Now, if you put the theory together carefully enough, in other words, choose the right number of these multiplets, you can achieve anomaly cancellation. In theories with twice as much supersymmetry to 0, requiring that there are no spin 3/2 multiplets, the anomaly cancellation chooses a unique theory, which happens to be type 2b compactified on K3. So here we are very far from being unique, and anomaly cancellation, as I said, is possible. It's not 0 on the nose. So what we try to achieve is a factorization of this type. So alpha runs for number of tensor multiplets plus this tensor field in the gravity multiplet, so nt plus 1. And this is some form on the space symmetric product on the space of tensor fields. And if we do achieve such a form of the anomaly, so the necessary condition, again, I'm not spelling out the conditions on the multiplets or the couplings. They are well studied. But yeah, so if we achieve this form, then we can introduce Green-Schwarz Sagnotti couplings in this form, and the anomalous Bianchi identity, whereby dH is related to this four forms. I will show them in a moment, sort of completes the job. There are numerous known constructions. Probably historically the first was the compactification of heterotic spring on K3, first perturbative, which means following the tactile cancellation and requiring the gauge heterotic instanton having a charge total charge 20, or total C2 equals 24. Of course, we have lots of choices for different embeddings or different instanton choices. Okay, and then we can actually replace one of the instanton by 1 5-brane or more instantons by more 5-brane subject to this constraint and obtain non-perturbative heterotic vacua with many tensor multiplets. There existed also quite a few perturbative deconstructions, of which probably the pioneer was Augusto Sagnotti, who spoke earlier this morning. Finally, there is F theory. So, if you notice the numbers showed by Peter in his talk, normally F theory provides much vaster space of sort of possible examples. But the thing which sets it apart from other cases, it also it comes with a very clear geometrical bound. So if you don't know much about F theory, you shouldn't worry, you will not learn about it from this talk. For purposes of this talk, I should say that physics of F theoretic models is completely summarized in the geometric information about elliptically fibered Calabi-Yau threefold. And all Calabi-Yau threefolds have some kind of elliptically fibered, some kind of bound, geometrically known as Cadieuler condition. It can be translated into conditions on physical couplings. Okay, depending on your taste, you might find the bound, let's say, not particularly convenient. Certainly, the bound is not very strong. It's a sufficiently rough condition. But the fact I want to emphasize that it exists. So for all F theoretic models, there is a bound. If I translate it to physical couplings, one can also test and check that among both string theoretic constructions like this, there are models which do violate this bound. The bound is too strong. You wouldn't be imposing it as a consistency condition on 6-dimensional theories. Okay. Now, on top of all this, we also have lots, let me call it for the moment, just simply anomaly-free supergravity models. You just put things together sufficiently carefully, and apparently you can do it in infinite number of ways. Here, for example, is an example. So K can run from 0 to infinity. Okay. And these kind of things do not have no string theoretic realization. So every time we see a situation like this, of course, it is a bit of an existential question. So is it difficult to realize things string theoretically, or is it impossible? If the answer is difficult, then we might sort of say, okay, maybe overcoming these difficulties will come with rewards. We will be learning about new mechanisms. It's good to know whether it's when it's impossible so that we don't break our heads. Of course, impossibility opens to other possibilities. One should consider whether it's insufficiency of string theory or whether this is inconsistency of supergravity. Now, I myself will not be hiding my sympathies. I will not pretend to be an impartial judge of this. From other side, okay, I mean, what we want is not just by our biases to dismiss an infinity of theories. We want to find some way of doing it scientifically. So, the question is, I mean, this is already much more constrained than your average supergravity because of anomaly cancellation. But one can ask a question, do there exist extra consistency conditions that should be imposed in order for anomaly-free supergravity be actually a candidate theory for theory of quantum gravity? The answer to this question is yes, and it was given in a nice paper by Kim, Xu, and Waffa, and I apologize, I don't have references on my transparencies. I will be happy to provide them otherwise. And the criteria is unitarity of Walsh-sheet theory of an object which they call supergravity string. So, word of warning, I will be talking about strings and I will be talking about 4-0 strings. This is not string theory. These are just BPS objects in your supergravity spectrum. So another point raised by Dieter that many tests that exist in literature, these are simply tests of string theory satisfying the swampland conjectures. So this is all done by known string theoretic means. Okay, so we are imposing some conditions just coming from within the supergravity. Okay, and I mean, these people not only answered this question, they also provided the criteria. But okay, for the moment, let me say that the purpose of this talk would be to present them in a more geometric system. Okay, so here is a rough cartoon which one could imagine for the moment. So the space is not bounded. There is an infinity of 6-dimensional supergravities with this number of supersymmetries. Anomaly cancellation cuts a big slice off or on, depending, but it's the number of anomaly-free theories is still infinite. Okay. Now, there is this domain which I called F theory. If you notice, I put a boundary around it exactly because of this codiral bound. So everything which is inside this zone does satisfy some geometric bound. And then there is another blob, which roughly are all the other consistent theories. So if you wish, what I want to do is I want to somehow also surround this area by some boundary, and I want to see if I can find something common. And of course, one is always hoping for surprises. All right. So let me start by just quickly telling you what the proposed bound is. Okay. So this is your average supergravity without being very concrete. So it has an anti-tensor multiplets. It has a Young-Mills multiplets with some group G. Generally not semi-simple. It can have U1 factors, it can have non-ability factors, and there are hypermultiplets in different representations of the gauge group or neutral. Okay, so, and the assumption is that, okay, we have tuned it up sufficiently or we've chosen the field content carefully enough so that this condition is satisfied. Okay, that we do achieve anomaly polynomial factorization. And here is the form of this. Notice that these are the same axes because of self-duality. So because these H fields satisfy self-duality condition, the Bianchi identity is also an equation of motion. And what X is, it's a 4-form polynomial, just typical for anomalies. So trace R square piece and trace F square piece, and these constants alpha and beta, which appear in the polynomials, they depend on the field content. Okay, once you compute the polynomial, you know these constants. Now, what do we want to do? We say, okay, this theory does admit dionic BPS objects, which are strings, with, I mean, they are charged under H. So here is a source equation. Okay, you can count codimension. This is a 4 form in 6 dimensions. It's a codimension 2 object, and it's also, it's codimension 4 object, and it has two dimensions of the wall volume. So it's a string. Okay, so Q is the charge, and because of these objects, in presence of these objects, we do modify the Bianchi identity. Hence, we also modify the equation of motion. Now, what it leads to, of course, it leads to modification of the anomaly polynomial. Next step, I would be using, okay, I should say probably one word. You see, normally, when we have just couplings like the Bianchi like that, that assures the validity or of Green-Schwarz mechanism. Having a source term to a gravitational coupling of the type like like shown here, somehow breaks. So notice that this term is good under both diffeomorphism, gauge transformations, and the shift of the B field. But in the presence of this of the source, this invariance breaks down. So this source sort of creates a non-invariance under the classical symmetries of the theory. But from other side, since the wall volume of the string is chiral itself, sort of we can achieve anomaly cancellation by an inflow mechanism, where the inflow of the anomaly from the bulk is cancelled by the anomaly of the 4-0 chiral string theory. Chiral theory on the wall sheet of the defect. Okay. I will decompose my SO4, which is 4 stands for the 4 transverse dimensions, into 2 SU2s. I'm also using tone isomorphism, which just simply states that, okay, if I pull back the source, the Poincaré dual of the brain, to the wall volume, I obtain an Euler density. So you can play a little bit on Euler density of the normal bundle and the Pentragians and how they react to this decomposition of SO4 into 2 SU2s. Here is an answer. Okay. And now you say, okay, I want to fix my central charges in such a way that this anomaly, which I have in the bulk in presence of the brain, which flows into the brain because of the delta function source, so should be cancelled. For that, I need to tune up the central charges. I mean, it's easy to see this central charge, for example, that the difference of central charges should be proportional to the coefficient of the gravitational coupling in the Green-Schwarz term. And it's also easy to see that, okay, we are dealing with supersymmetric 4-0 model, that the only part of the theory which is aware of the normal bundle or about the SU2R symmetry is the part which has supersymmetry. Because it's only the supersymmetric fermions which are sections of this SU2 bundle, so they transform under the wall sheet R symmetry. One way or another, okay, I determine the central charges. Now, okay, there are both constraints on the admissible Qs. I mean, we want to have well-defined moduli space, we want to have non-negative tension and things like that. I will not be taking you through this list, but okay. Reasonable constraints on the bulk theory I need to impose, they constrain Q slightly. Here comes I have done this. This is the condition that we have to impose for consistency. So what does it state? I already told you what the central charges are. And the left-moving central charge, and this is the interacting central charge, so I'm subtracting 4 for my center of mass, has better be bigger than the central charge of the current algebra, which couples to this string. So I have plenty of gauge fields. There is some current algebra which couples to the string. If these two, so I have two different notional central charges. I am computing them in two different ways. But in unitary theory, I better have the central charge bigger than the central charge of the, or equal, than the central charge of the current, the Kasmudi current, which I am coupling from the brain. So here is my constraint. Whereas the conjectural part is, I would say, look, I mean, see, this central chart C left depends on Q's, quadratically notably. I can always scale Q's up to be large enough to satisfy any bound, anything that my current algebra will give me. And there is this string completeness hypothesis, which tells us, no, you are not allowed to do this. All admissible values of Q should be somehow covered. So if this relation breaks for a single value of Q, typically a small value of Q, that's already an inconsistency. Okay, so here is the bound. It has been studied. Notably, it has been shown how many theories with this infinite number, I mean, you understand that for string theories, this is a particular affront to have theories with infinite rank of the gauge group. Clearly, we cannot find them in string theory. So many of them were shown to be inconsistent, and they don't pass this criteria. Now, what do we want to do? I mean, I somehow promised that I will rewrite this and I will do it slightly differently and hopefully present a better packaging. Now, I'm not going to do anything different. I'm going to do exactly the same, as a matter of fact, except to do it in 5 dimensions. So I take that 6-dimensional theory, I put it on a circle, I re-examine. Now, you might say this is a kind of dumb thing. Obviously, the inconsistent theory in 6 will be inconsistent in 5, and vice versa. Well, that's the reason I'm doing it. The second reason I'm doing it is that I will argue now that actually 5-dimensional theories, I mean, very much related by simple circle compactification from 6, have an extremely different way of packaging information. So what I'm hoping for is that just writing pretty much all the same, or doing the same analysis in 5 dimensions is actually might turn out to be more helpful. So here is the probably, I mean, less technical or whatever, easiest way to see what I mean by packaging information in different ways. So let's consider M theory fibered on elliptically compactified on an elliptically fibered Columbia, as opposed to F theory compactified on the exactly same Columbia. And see what I mean by packaging of information. So in 5 dimensions, there are a set of supergravity couplings, such as Simon's couplings. They run over the all, this index B, index I, J, K, runs over all the vectors in 5-dimensional supergravity, which in 6-dimensional language covers the tensors, the vectors, plus extra that you get from reduction, Kaluza-Klein. All I need is the intersection form of the Columbia, and all the Char-Simon's coupling are there served to me on a plate. If I look at 6-dimensional this theory, I see only a fraction of this. I mean, in a simple, transparent way, I see only a fraction of this intersection form. Okay, I only see a couplings between 1 B field and two gauge fields. Okay? And this missing information actually requires a 1-loop string calculation. Two central charges behave very differently. I mean, I showed you that, again, fixed by anomaly inflow, that while in 6 dimensions they are quadratic, in 5 dimensions they are generally cubic, and they do miss the quadratic part. Okay, now, there is a heuristic argument why the passage from 6 to 5 has to be non-trivial. You see, in 6 dimensions, I was talking about anomaly cancellation. So there is a Green-Schwarz term. These terms are by design not gauge invariant. They're designed to be no, and when I say gauge, I mean gauge and diffeomorphism and all symmetries. Okay, these are not invariant terms by construction. You reduce them on a circle, they will continue being not invariant. On the other side, 5-dimensional theory does not have anomalies on its own to cancel these non-invariances. So what's going on? What's going on is that, okay, not only I expect the 1-loop, so I have to integrate massive modes in the circle when I am compactifying to 5 dimensions. This is a one-loop calculation. And the claim is that there are very non-trivial contributions from all the chiral fields, all the massive modes coming from the chiral fields of 6-dimensional supergravity. Okay, so these new contributions, they are not only going to provide me with the missing information on the intersection forms, but they are also going to somehow cancel the non-invariance of the reduced Chern-Simons term. And if you check it in details, you see that the conditions for this to happen is exactly the same as condition of anomaly freedom in 6 dimensions. We have a slightly different take on this with Peng and Stefan. Just take the anomaly polynomial, okay, for simplicity. I mean, you can think of it just in global gauge theories. Write the anomaly polynomial and I mean, construct it with an isometry, okay, integrate along the fibers. So reduce your anomaly polynomial. You can show that the reduction actually is given by a variation of some object, which is a trace of the Wilson line times something which I call X. Now, people who know anomalies from old days, so this X is derived from Bardeen's Zumino polynomial. So this is something which allows you to interpolate between covariant and consistent anomalous currents. Okay, if you don't know this, if you don't recognize it, it's not important. The main thing you need to know about the Bardeen-Zumino polynomial that it's a local object. Okay, so in other words, what I'm saying, and this is a completely scheme-independent statement, is that the reduction of the anomaly is given by a variation of a local object. Not surprisingly enough, we are in odd-dimensional theory. Every odd-dimensional theory can be fixed by adding a local counter term. So take this guy and I just subtract it. The problem is that by doing so, I am severing the ties from its 6-dimensional parent. Okay, so I can fix the theory, but I cannot go back anymore. It's only in the cases where there is a different counter term possible, and that counter term can be lifted to Green-Schwarz terms, when I can have both the cancellation of these non-invariances and liftability. Okay, so in that sense, anomalies are also providing an obstruction to liftability. Okay, so I'm done somehow motivating why I'm not completely crazy by looking at 5 dimensions. How am I doing with time? Okay, so one case which is kind of particularly nice to study, for example, I could look at, and I can compute, how the graviphoton couplings are generated. So this object did not even exist in 6 dimensions. Now one can compute, and this was done actually not by us, it was already done before. There were some subtleties about the overall coefficients. Okay, that yes, indeed, the Kaluza-Klein vector does, I mean, for it, you do generate a triple self-intersection. So there is an AFF term just before this guy, and then there is also a gravitational coupling. Now, if you look at this guy, the anomaly cancellation becomes very, very different from the 6-dimensional case. So this object is relatively simple. Once more, by inflow, I will get a pullback of the gravitational anomaly. So, and it's always going to be, this KR is always going to be proportional to differences of central charges. The other question is that, okay, how do I deal with this guy? And that requires a bit of a song and dance, so you need to smooth out your delta function, choose a different representative of tone class, and use this remarkable formula which relates the integration along the fibers of the cube of the global angular form to contraging numbers. So I just wrote, I mean, this works for any degrees of even global angular forms. All I need for now is just E2 and P1. Okay. So, but you see, because the cube here is related to this guy being cubic, so the central charge which I derived by inflow ends up being cubic. But actually, I'm not interested. I mean, the constraints for these objects turn out to be much weaker. I'm not interested in new objects which I create from the reduction. I'm interested in objects which I already had, okay? And I go back to the string which I had in before, and now I say, okay, what happens to the reduction? So I had the transverse 4 dimensions. Now this transverse 4 dimensions becomes a bit more special because there is a circle, okay? So what it amounts to in language or formula is somehow you need to identify the two SU2s, okay? And once you do it, you see the Q dependence will be dropping out because of different signs. So the net result is I'm going to get something which is linear in string charge, okay? If you do it sufficiently carefully, you extract the interacting part of the left moving central charge, and you find this formula. Now, why should one be yelling Eureka or Kodaira in this case is this magic coefficient 12, okay? To F theory and Kodaira. So there is a bound which all theories, all models which come from from F theory compactifications do satisfy. So there is some easy dictionary which was discussed in detail, notably by works of Morrison and Taylor and collaborators, how to go from kind of physical constants to Calabi-Yau data. Okay, in physical language, okay, here is some condition that these coefficients A's and B's should satisfy. It comes from a geometric bound, which simply says that, okay, I mean, this is, if you wish, a condition for an elliptic fiber over a singular Calabi-Yau or over a singular Kähler manifold, 4-dimensional, to give me an overall Calabi-Yau space. So I want to achieve an overall C1 equals 0, okay? And it states that, okay, this is the canonical divisor. These are all the different singularities. So this number X is very important. It's, okay, you can think of it as number of D6, or you can think of it as multiplicity of singular divisors. Okay, and then there is this guy called residual divisor, and Kodaira showed that this better be effective. And effective means that its intersection with any divisor of certain type, again, I'm not telling you what left divisor is, or I could invert it and say left divisor intersects every effective divisor positively or non-negatively, okay? So here is the bound I'm talking about. Okay, so all F theoretic models have such a bound. And once more, notice this remarkable number 12. Okay, so this is the one which made us very, very happy, because now we can take and compare directly with our condition, and notice our condition was this. Now, for Kodaira, there was this set of numbers X's, which you can just read off from the Kodaira table, which is very well reviewed in many, many places. Here you see, in general, I would have something which really still depends on the theory. Now, you can see that if I replace this Q dot D by 1, I get the strongest version of the bound. And then all of a sudden, this guy becomes just group theoretic factor. I can just compute it from sort of from the group, from the singularity structure. Of course, there is a price to pay if, let's say, I find a model which fails to satisfy this condition. I should go and re-examine it a little closer, because it does not necessarily yet signify inconsistency. I should be able to verify first that Q dot B is not necessarily bigger than 1. Okay, so but, once more, we are just looking for crude bounds. So I take the strongest condition, and here it is. Now I can write it in this form. And now you can, okay, if I geometrize the physical, so it's not a priori evident there is a Calabi-Yau to which I am applying this. Okay, but I'm saying let's assume there is. If I geometrize it, I will obtain a bound of this form, and once more, y is written here. Now you can see that x, the Kodaira's the multiplicities of singularities is always the bigger number. than this y. And actually, all the models are of two types. Either, okay, there is either it's more than, well, okay, you see, either the difference is bigger or equal than 2 or smaller for very few groups. So now with this, okay, this is not directly comparable yet, but you can say, and we prefer to work somehow in geometric setup. Once more, we could have just worked with A's and B's. So let's assume that there is a labial and see what these two relative conditions give us. Okay, so we can compare them and we can compare them systematically. And what we find systematically that in vast majority of examples, very easy necessary condition would be that there are at least 3 gauge groups intersecting our divisor is satisfying Kodaira condition automatically leads to satisfying the unitarity condition. Okay, again, vast majority of the cases. It can happen only if we have 1 or 2 gauge groups intersecting this divisor, where actually the unitarity condition is stronger than Kodaira. One of these examples was already discovered by Kim, Xu, and Yao. What we are doing here is somehow systematics. So I claim that these are all these cases where it is possible. It's a bit technical. I'm not going to take you through the analysis or even the results. And you can even show that, you can find non-trivial examples, and you can see that for some anomaly-free models, indeed, numerical equivalences, that means d dot y being 0, would not be compatible with elliptic migration. So for these models where the unitarity condition ends up being stronger than Kodaira, again, in general, it's weaker, so, which goes well with our intuition that there exist consistent theories of quantum gravity which do not come from a theory. They come from other constructions. Okay. On the other side, there are cases when it's stronger. It means one of the two things. Either in those cases, there is no underlying labial. So those models either do not have a theoretic realization, or they may have it, but somehow there is a more refined structure of the singular divisors for these particular models, which Kodaira does not detect. It's too crude. Okay, so we may end up learning a thing or two about elliptically fibered labials. So with all this, I will be finishing just by showing you some kind of refined version of my earlier cartoon. I mean, it's not really shown in scale. So this bright color, okay, once more, the yellow zone, or whatever this color is, these are the models which are anomaly free, but they don't satisfy a bound. Okay, so we think they should be in the swampland. Now, as you see, I have shown a boundary around the whole zone of the consistent theories. And the F-theory models I have placed inside, and even further inside in the interior, I have placed this brighter area where the unitarity condition is stronger than Kodaira positivity. So in a sense, if you wish, you can think of this picture as if I'm moving from the interior of the consistent zone towards the boundary, the conditions, the consistency conditions become weaker. Okay. So that's in sense in which, again, really kind of cartoonishly, that's the way in which I have kind of arranged all these theories. But the important thing for us is that there are sort of bounds. I'm sure, okay, once more, this was a very, very tiny corner of the swampland program, of which I'm not an expert. But for even 6-dimensional problems, or a much larger sense, I think it's a kind of a fascinating question, which has been sufficiently fruitful, kind of trying to ask the questions in a slightly different way than we were used to be by fiat declaring string theory models to be good, and anything which is not so good, to try to really find some kind of general bounds on the consistency of the theories. Thank you very much for your attention.
Thank you, Ruben, for a very nice talk. Questions in the auditorium? Ioannis?
Hi, Ruben. A question about this unitarity constraint. This is basically a constraint on the two-dimensional CFT, right? That lives on the string.
Yes.
Could one imagine that in a strongly coupled string, this may be violated? You know, I'm thinking of a string that simply chops off pieces of string out to the bulk and so on. Is this a weakly coupled string constraint or not?
You mean in strongly coupled theories, you envision violating this relation between central charges and yet having unitarity?
Well, because it's not a 2D anomaly condition, it's simply that the central charge you said should be bigger than the central charge of a Kac-Moody algebra.
Right. Right. So I guess the assumption is that there should be always a, let's say, a sufficiently nice regime where you do expect this to hold. But yeah, maybe there is some assumption. At least I don't know counterexamples.
Thanks.
Any more questions in auditorium? No? Online? Do we have questions?
There was something, no?
No, that was you.
This is me?
Yes. Okay, if there are no more questions, let's thank Robert one again.
Thank you.
Good night. Lunch breaks, you are back at 4 o'clock.